All right, so this is the first lesson of Unit 3, nuclear chemistry. We're going to discuss nuclear radiation, its penetrating power, which you just saw in the video, what nuclear stability is, and the band of stability, which really determines what atoms are naturally stable or unstable. So there's a couple important individuals I want to mention. I was not going to mention this guy, but his last name is very significant. William Röntgen. 1845. You don't need to know his birthday. I'm just adding it. 1923. He is famous for discovering X-rays, which is a major form of radiation. When we watch Chernobyl, you're going to hear the word Röntgen said a lot. It is a measurement of the emission of ionizing radiation. You're going to hear like 3 Röntgen, 8 Röntgen, 15,000 Röntgen. Obviously, the higher the number, the worse the ionizing radiation is. And ionizing radiation is the stuff that will just tear your cells and your DNA apart. There are literally people from Chernobyl that like melted. It's not a pretty picture. So that's why, obviously, you need those permission slips. Okay. So what does Jackson? Put your phone up, right? You have your phone in your lap? Okay. All right. So you're going to hear the word Röntgen a lot. He's a very, very famous scientist when it comes to nuclear chemistry. And then the woman that put a lot of female scientists on the map, Marie Curie, 1867 to 1934. She discovered radioactivity. Oops. Remember that radioactivity, that is one of your terms, is the process of atoms releasing radiation or emitting radiation. Curie's work led to a new field of science, and we call it nuclear chemistry. And I remember seeing this on a Jeopardy question one night a couple of years ago. Curie discovered 2 radioactive elements. Polonium, which is abbreviated PO, and yeah, radium. So it was not radon, it was radium, which is Ra. She discovered those. All right, so I actually did find some pictures of these people. Let me pull them up here. Here's William Röntgen. And then here's, where is she? There she is, Marie Curie. Two very important pioneers in the study of nuclear chemistry and nuclear physics. All right, next topic is something that we actually did, I think, on Tuesday. So it should hopefully still be fresh in your mind. Types of radiation. I don't expect to spend a whole lot of time on this one because you just did get this the day before yesterday. How many types of radiation are there? There's 3 types of radioactive particles. What is the biggest and the bulkiest kind? Alpha particles. The symbol for alpha is either the symbol for helium or the actual Greek letter alpha. It is made up of 2 protons and 2 neutrons. It has a positive 2 charge and is minimally penetrative. Because it is so big, it really can't penetrate anything. I mean, a sheet of paper that you are writing on could stop alpha particles. If somebody had a gun and it could shoot alpha particles at you, let me tell you how you would protect yourself. Just like this. They're so big they can't even go through paper. What is the second type of radioactive particles? Beta. You can either use the electron symbol or use the Greek letter beta. They have a -1 charge. And they are moderately penetrative. They can go through paper. They can go through plastic. It really can't go through metal or concrete or thick clothing. Yes, Varun. Not really. And then we have the most powerful of them all, gamma rays. You got the Greek letter gamma. They have no mass, no charge. They are highly penetrating. That's the Greek letter gamma. It looks like a weird looking Y. It takes several feet of concrete or even lead to contain it. This is why most nuclear reactors, which is the core of a nuclear power plant where the nuclear reactions are happening, they are encased in several feet of concrete with layers of lead put in the concrete to try to keep all the radiation from to prevent it from escaping from the buildings. When you see Chernobyl, the big problem was that lead-lined wall was blown apart and everything could just leak out. That was worst nuclear disaster in the history of this planet. It's pretty bad. Your parents were definitely alive. When we're talking about it, you might want to ask them. You know, they might have been in high school when it happened. You know, say, what was it like when Chernobyl happened? I asked my dad, who was in his 40s, and he was like, "Oh, we thought we're all going to die." Because they're like, "Oh, Europe's going to be wiped out, and then it's going to come over to North America." But they were able to. It was just a different time. It was the Cold War. It was USSR versus America. Obviously, USSR doesn't exist anymore. So there was a lot of politics involved in it too. And that show will display all that. Okay. Let's get to nuclear stability. I want you guys to try to finish this statement. Atoms emit radiation to what? Why do they emit radiation? Varun, I wish everyone was more participatory like you. Go ahead, Madeline. Bingo. To become more stable. That's the name of the game. Their nucleus is too big. Do you recall what I said earlier? If they're unstable, what do they tend to have too much of? Protons or neutrons? They tend to have too many neutrons, and it makes the nucleus unstable. Radioactive decay involves the conversion of an atom of one element to become another element. There is a name for this. This is called transmutation. It's a vocab term. This is what alchemists wish they could have done. Can you turn something very common like oxygen and turn it into gold? That would be incredible. You would be an automatic trillionaire. This isn't entirely like that. What you're doing is you're turning in a nucleus, which is way too big, like uranium, and making it a little bit smaller, like thorium. And then thorium can break down into, say, polonium. So things can become smaller and smaller and smaller until they do eventually become stable. But whenever an element is giving off decay and it becomes a new element, that's called transmutation. Next term is going to be nucleons. This was mentioned in the video. A nucleon is simply a subatomic particle found within the nucleus, and you should know what those are. That is nucleons. What are the two subatomic particles that are found within the nucleus? Neutrons and protons. Electrons orbit the nucleus, and so they don't count. A nucleon is a neutron and a proton. And as mentioned in the video, what force forces the protons to stay together despite the fact that protons, one proton and another proton, are positively charged and they don't want to be with each other? Did you recall from the video what that is? It's called a nuclear force, or a strong nuclear force. Protons repel other protons. Chris, why does a proton repel another proton? Exactly. It's not complicated. Like charges repel each other. There's a term for this, and I think Varun or someone said it recently. It's called electrostatic repulsion. The opposite of this would be electrostatic attraction. So if Chris was hanging out with James and they hate each other, they can't stand to be with each other, but I force them to stay with each other, my strength is outweighing their strength. It's outgunning theirs. There is a force that is stronger than electrostatic repulsion, and it is called a strong nuclear force. The strong nuclear force generated by neutrons overpowers the electrostatic repulsion of protons. Guys, these are a lot of big, complicated chemistry words: electrostatic repulsion, nuclear force. Just understand this. An electrostatic repulsion force is strong. but a nuclear force is stronger. And it forces those protons to be together even if they don't want to be. If you take out the neutrons, the protons will just scatter. But the neutrons are very, very important to keep the nucleus intact. So the strong, if you want to write it, it's like a math equation. It could look like this. Strong nuclear force is greater than electrostatic repulsion. It's as plain as that. Jackson, if you're on the football team and you just can't stand Aiden, I'm not saying this is a true story, but you're on the football team, he's on the football team. I had a kid when I played tight end in high school. I hated our quarterback. I mean, I'm using the word hate here. Hated him, but I had to get, I'm the tight end, right? Whose passes do I catch? His. I got to deal with him. So I might not like him and I don't want to be with him, but there's a force that is making me be with him, making me work with him. The electrostatic repulsion could make him go the other way from me and me the other way from him, but the force of the team and the needs of the team kind of just make us work together. Dude, Jane, I hate this guy. You ever have a court? Is he the quarterback? He's quarterback? What are you? Stop it. Yeah. Are you 81? That was my number 2. What's your number? 5. Okay, the other kid's number was 14. Are you the kind of quarterback that says, hey, I'm a quarterback. You want to touch me? I'm a quarterback. Hey, Garrett, you want to buy my lunch? Would you feel better about yourself if you bought my lunch? Because I'm most definitely. I am the quarterback. You want to sign you want my autograph? He was like that. Horrible kid. And when do you play defense too? You know, playing defense, I went both ways, defensive end. So when we got a scrimmage, put him on his back. All right, let's keep going. This is gonna look good on the YouTube video when you guys play it back. Okay, let's keep going. What time we get out of here? 58 after. Sheesh. Okay. I think we'll have to stop here because the bell's gonna cut me off. I'll